Okay, good. All right, so we're going, just had some little technical issues because my software updated. All right, now I think everything's good. Okay, folks, so today the plan is to discuss the Bourne Approximation. We're talking about scattering. And so I just want to draw the picture. This is our picture for scattering. And so we have some little area here, d sigma, and we have a potential here, V of R, and we're sending in some wave. It has some incident wave. This is the picture you should have in your head. That's the incident wave. And that scatters off of this potential. And so I draw a sphere around that spherically symmetric potential, and I consider scattering into some solid angle, and then I get scattering into the new state, which I'll call my final state, which I'll draw it right here. Psi final is equal to 1 over L 3 halves e to the I k final dot R. All right, and so that's the final state where L is just equal to the size of the universe, just to put everything in a big box. Size of universe. And this angle is my scattering angle, theta. And this is d sigma, the solid angle that I'm scattering into. And then I sort of think of myself as this scattering angle. I just want you to get some sense that I'm scattering into some solid angle d omega. I'm having trouble drawing it because it's all three-dimensional, but I want you to get some sense that we're shooting out into some d omega, some possible solid angle that is then integrated over the iris because of the symmetry, because of the cylindrical symmetry. This is due to the cylindrical symmetry. And so what we do then is we say, we know that from an experimental point of view, from an experimental point of view, if we think of this classically, like if I was shooting in BBs, little balls, then what we would get is, we would say we can define this quantity d sigma d omega. The differential cross section is going to be 1 over the luminosity times dn times d omega, where dn, where L, the luminosity, is the number of particles per time per area that are incident, dn is equal to the number of particles per time that go into the detector, where this is my detector, and then I have dn equals the number of particles per time into it. And the detector spans some solid angle d omega. And so this is just then the size of the detector. The detector spans that solid angle. And so that's sort of the fundamental definition of scattering, how all the various quantities fit together. And that was pretty easy to derive. Then we generalized to quantum mechanics. And that was actually sort of straightforward. We just say, we just basically we replace the word particle with the word probability. In which case, we can then say that d sigma d omega is equal to 1 over j incident times dr over d omega, where j incident is now just probability per time per area, and dr is, instead of particles per time, it's probability per time that goes into my detector, and d omega is just, once again, the size of the detector. So everything is kind of the same, except I just replaced particle with probability. And so then to find d sigma d omega, and we did this last time, I did it really fast, so this is review. I realize this is review, but to find d sigma d omega, then we have to find j, the incident probability flux, and we have to find dr, the probability per time. And so the way we did it was, from the probability flux, we used this formula, our little old friend from last semester, psi star del psi minus psi del psi star. And for this, we just use Fermi's golden rule. Fermi's golden rule. And so from these, when we do the math, J incident is easy. You do the math, and it's quite simple. You just plug into that formula, and we did it last time. I won't redo that. It's equal to h bar k. So we're taking the magnitude. It's h bar k over m L cubed, where L is the size of the universe. And that comes from normalization. And then from Fermi's golden rule, we have that dr is equal to the constant 2 pi over h bar times the matrix element squared, where the matrix element is basically the perturbation, which is the potential, the scattering potential, which links the initial and final states, which are momentum eigenstates in this case. So these are I just want you to remember the incident and final state. This is here I have them. That's the incident state, and that's the final state there. Okay, and then we have to multiply times the density of states, the density of final states. And so here we have this is the initial state, the final state, and this is the density of final states. And here, the hard part here actually is the density of states. And I went over this really fast last time, but I just want to say that the density of states, the picture that you should have in your mind is this. I have an initial state, K initial, and then the final states, I hit the potential, and all the possible final states I could scatter into any of these directions. So I have 4 pi of solid angle. That's 4 pi. But I don't go into 4 pi, I actually go into some specific solid angle that I'll draw it as a cone, but it's really like the iris of your eye, but I'll call it d omega. And so that means then that this, if this is the total density of states that takes me into 4 pi, then the density of final states, d rho, is going to be equal to the total density of states, but only a fraction of it. And that's going to be d omega over 4 pi. So that's an important concept, which I think is straightforward when you think about it. It's just a ratio. I'm only going into one part of the total solid angle defined by d omega. So it's just a ratio there. So I have d omega, or d, the little differential density of states is equal to d omega over 4 pi times the total density of states. And so then we have to write the total, we have to figure out the total density of states and define, and sorry, I kind of raced through this last time. And I guess I'll sort of race through it again, but I just want you guys to, the concept of density of states is so important. I would just want you guys, I think it's important for you guys to see that maybe a few times. And so we've already did it, I think in one dimension, we did it already for an example, but now I need to do it in 3 dimensions. And so let's remember in 1D, we look at a box of length L, and we fit our states into that box, and we say that L is equal to n lambda, and so lambda is equal to L over n, and so K is equal to 2 pi over lambda, so Kn is equal to 2 pi n over L. And so then we so we know that our states are quantized in momentum, quantized. And so then we have delta K per state is equal to 2 pi over L. And so then we have the number of states per K is equal to L over 2 pi. And so I can call that the density of states in K space. Density of states in K space. And so then what we can do is we can say that if I have a dispersion of states where this is E and this is K, and if I have some little range of states in K, then they correspond to a range of states in energy. This is energy, and this is some range of energy, and then there has to be a relationship. We have the density of states, the total number of states in the energy axis is rho density of states times dE, and that has to equal the total number of states on the momentum axis, because there's a one-to-one correspondence. There's a mapping from the states in momentum to the states in energy. So in my mind, this is the most important relationship, is to understand that. And so then what we say is, we say that rho of E is equal to d of K times dK dE.
Professor?
Yeah.
Quick question. Is there any reason why you drew it as a parabola?
Oh, yeah. Because we're talking about free particles. And so for a free particle, then energy is equal to P squared over 2m.
Oh, I see. Okay.
A squared K squared over 2m. But you do raise a good point. I mean, out in the real world, the dispersion could be much more complicated, because I could have the electron traveling through a crystal. It could be traveling through a crystal of copper or silicon, in which case the E over K relation, the E versus K relationship could be quite different. So that's a good point you raised. But we're just talking about free particles. And so we have this very simple problem. Okay, and so now in 3D, we just generalize this concept And we have the same relationship, only now there's a little glitch, because now in 3D, we have this, we still have this parabola. The energy versus K relationship is still a parabola. And so we still have this concept of a dk and a dE, but now the complication is that my K is three-dimensional. And so now I have a Kx, a Ky, and a Kz. And so now we have K is quantized in the X direction and the Y direction and the Z direction. And so we have a three-dimensional grid of K states. And I can't draw it, you know, it's hard to draw a grid for me, but it's there. And so when we look at the K states that correspond to this dE, so I have this dE, but the K states that correspond to it now are living on a sphere. And so the dk is this eggshell. So it's the states in the eggshell, not in the interior, but in the actual shell itself. This is the shell. I'm cross-hatching it right now. So it's the states in that little shell. And those are the states we care about now. And so those states, so now what I do is I have, when I equate this, I have to say that the density of states in energy, d rho e dE, is now equal to the density of states, is now equal to the states d of k, where this is a three-dimensional density of states in k space, times d cubed k, which is the volume in k space, and that's the difference. But now the volume in k space for this particular situation, I say that d cubed k, it's that eggshell, so it's the volume of the eggshell, and so the volume of the eggshell is 4 pi k squared dk. So it's the area of the eggshell times the width of the eggshell. So that's, so then, and the three-dimensional d of k is, well, if the one-dimensional d of k is here, we actually derived it very quickly, it's L over 2 pi. Can somebody guess what the three-dimensional d of k is? I'll give you a hint. It's just the density of states in the x direction times the density of states in the z direction times the density of states in the y direction. And what is each of these factors?
L
L over 2 pi.
Exactly, that's gonna be Lx over 2 pi, Ly over 2 pi, Lz over 2 pi. So what's the density of states in three dimensions? Somebody tell me.
L over cubed.
Exactly. Because we're just going to assume that the universe is a square box. All right, Lx equals Ly equals Lz. That's a reasonable assumption to make. And so then we had it. So then we have rho of E dE is equal to this thing, the density of states in three space. It's this formula, L over 2 pi cubed times, now we'll take this formula here, 4 pi k squared dk. And so then I'll bring this guy underneath, and I have that the density of states in three dimensions is equal to L over 2 pi cubed times 4 pi k squared dk dE. And that's the density of states in three dimensions. There it is. And we can go a little bit, we can take it a little bit further. It's pretty straightforward because we know that dk dE is equal to dE dk inverse which is equal to the derivative with respect to k of the energy, which is h bar squared k squared over 2m, right? Inverse. And so that's going to give me, let's see, that's going to give me m over h bar squared k. If I do my derivative right and invert it, yeah, that's it. dk de. And then we just plug that into here. And then we have rho of e is equal to L over 2 pi cubed times 4 pi k squared times m over h bar squared k. And so this k cancels, that k cancels, and some 4 pi's cancel. And I also have to use this since I have h bar squared k squared over 2m equals e. Then I have k is equal to square root of 2me over h bar. And so if I plug that in, then I'm going to get density of states is that final relationship that I think I wrote down last time, which is you get this answer. You get this. Did I write it down? No, I kept it in terms of k. Okay, so let me write it down. So here, so let's keep it. I'm not gonna. Let's keep it in terms of k. So I'll have ml cubed k over 2 pi squared h bar squared. Okay, so that's the answer. That's the density of states. And so that's a very famous answer. And so then we see then that the density of states, the scattering density of states, scattering DOS is d rho, which is equal to d omega over 4 pi times rho total density of states. So the scattering density of states will be equal to, I have to take this answer and multiply it by 4 pi, divided by 4 pi. And we get this result. We get ml cubed times k over 8 pi cubed h bar squared d omega. Okay, so that's the density of states factor. That was sort of the hard part. And so now we just plug it back in to that expression that we had, plug back in, and we're going to have, and I'll just remind you where we're going to plug it back in. It's, you want to plug it back into this formula. God, where is it? Way up here. Basically, yeah, we're plugging it all the way back into this formula. So we're going to plug everything back in. And so where was my Fermi's golden rule? Ah, yeah, here's my Fermi's golden rule. Fermi's golden rule. So let's plug, so we have that Fermi's golden rule. So from Fermi's, if we plug it back into Fermi's golden rule, then we're going to have Fermi's golden rule. We have dr is equal to 2 pi over h bar times this matrix element b of r k initial. And now we'll plug in that density of states. So we're going to have ml cubed k over 8 pi cubed h bar squared d omega. Plugged it all in. And so, Gori, oh, can you hold it down? That'd be great. Okay. And so then we have, we have we bring that d omega underneath, and so now we have dr d omega is equal to 2 pi over h bar. So I'm just plugging all this stuff in. I think it's useful just to see it all plugged in. I'm sorry if it's like a lot of tedious math, but I think the answer is really important. And so it'll be ml cubed k over 8 pi cubed h bar squared. Okay, and so now we've derived, so from Fermi's golden rule, we get this very beautiful little expression for the dr d omega, and now we go back to this differential cross-section definition here, and we see that the differential cross-section d sigma d omega is equal to 1 over j incident times dr d omega. And so when we just plug it all in, then we're going to get, well, I want to keep track of all the little factors, because I want you to see that this factor has an L. So that's the size of the universe. So that's sort of like that weird little factor that we added, to make the math work out. But I want you to sort of see how it all cancels. And so let's do it all. And so we're going to add, if we add those factors, then, well, okay, before we go into this, let's just take a quick look at this dr d omega, and let's keep track of all the factors, because what I can do is, if I move all these factors around, then I can see that dr d omega is equal to m times L cubed times K over 4 pi squared times H bar cubed times, now let's write out this matrix element. Because I want you to see all the factors, times this matrix element. Now the matrix element is an integral. It's going to be an integral of these three things. The first thing here is going to be the final state, 1 over L to the 3/2. I don't know why that happened. Times e to the minus I k final dot r, because I put a minus sign there because it's complex conjugate in the matrix element, times v of r times 1 over L to the 3/2, and now the initial, e to the I k initial dot r, d cubed r. And this whole thing is squared. That's the matrix element squared. All right, k final, v, k initial, squared is this whole thing, that whole mess. Now I want you to see this, dr d omega. I want you to see how this guy hits this, this guy hits this guy, and I get 1 over L cubed, right? And so you might think that he cancels the guy on top, but he doesn't, because he's being squared. So I end up with a 1 over L to the 6th, right? 1 over L to the 6th. So it's kind of like I'm going to get m k over 4 pi squared h bar cubed L cubed, because I brought a 1 over L to the 6th out. And now I'm going to get this thing here will be the integral of e to the minus I k final dot r v of r times e to the I k initial dot r. I think it's nice, it's fun to sort of see how all these factors work out. I think this is actually useful. But then you see that to get the d sigma d omega, I have to I have to multiply this factor, which is this guy, times 1 over j incident. And 1 over j incident is going to be ml cubed over h bar k. And that's going to multiply times the mk over 4 pi squared h bar cubed L cubed times this thing. And this thing here, I'm just going to call that my matrix element, K final, V of R, K initial, but I got to put a tilde over it. Why did I put a tilde over it?
Because you got rid of the 1 over L to the 3/2 in front of them. You got rid of the normalization. Can I ask a question?
Yeah.
For the K's in the J incident and the K's in the K and the D sigma, dr D sigma, those are different K's, right?
Well, let's go back and look at it. Way back. Yeah, okay. You see them in this picture? K incident is going to the right and K final is going up, right? Because like, you know, this is K incident and this one is, you know, K final. Do you see it? You know, K incident, K final. Do you see them? I'm asking you a question. Do you
Yeah. I see. So the first one would be K sub I, and then the second one is K sub F.
Yeah,
right?
because K sub F is going at theta, at the angle theta, right? You see it? This is theta right here. I'm circling it. Do you see that?
Yeah, that makes sense.
And but the thing to notice is, so I just want you to see that, you know, K initial, I'm writing up here in the upper right hand corner, does not equal K final, because, you know, K initial is this way and K final is that way. But what about the relationship between their lengths? What can you tell me about the relationship between their lengths? Are their lengths equal? Yes or no?
Yes.
Why?
Conservation of momentum?
That's an interesting thing that you just said. No, actually, but that was an interesting comment, because the momentum has changed. I mean, I got the initial momentum this way and the final momentum that way. So in some sense, the scattering is changing the momentum of the particle, right? So it used to be this way, now it's this way. So the momentum has changed.
Conservation of energy?
Yes, conservation of energy. Because energy is the wavelength, right? The wavelength. That's it. The energy is in the wavelength, and the energy is the same. Okay, because that's for elastic scattering, and this is elastic scattering. Okay, now let's go back to here, and so we see that so the thing about this tilde is that basically what I've done is, this is my matrix element for my initial state scattered into my final state, but it's when the universe has size L equals what?
1.
Yes. Because I took the length out. So now what I've done is that's basically the matrix element if the universe had size 1. Okay? It's just a mathematical thing. And so then this, I'll call this times, so here I have this K final V K initial here squared, but the little tilde, because now the universe, these are the initial and final states if the universe has size 1. And now notice these L's. What do these L's do? What do they do? What do they do? Somebody tell me.
They cancel.
Yeah, they cancel. Boom, boom. And that's beautiful because that means that this L, which was the size of the universe, this artificial parameter that kind of made no sense, is gone. Yay, it's gone. So that means that life is meaningful. Like once again, we were a little bit worried there for a moment, but now, once again, life is meaningful to us. And so we then get this very famous result. Let's write it all down, and it's glorious. It's this m squared. It's such a simple result. 4 pi squared h bar to the 4th when you factor everything in, and then I have this funny matrix element, which is not that funny. V of r, the potential, and the initial state. And I put the tilde over it just to remind you that this matrix element is for a wave function in a size of universe of L equals 1. But that's good because that means we don't need to introduce any weird factors of L into the answer. So notice that there's no weird factors of L. This is the differential cross-section purely in terms of the given parameters. Basically, it's in terms of fundamental constants. It's in terms of V of R and fundamental constants, right? M, H bar, pi. And so it's a beautiful result. And we give it a name. Does anybody know what it's called? It's an approximation. Anybody know what it's called?
The Bourne Approximation?
Yeah. We call this the Bourne Approximation for Mr. Bourne. Like,
Is it the only approximation here, the one that comes from Fermi's golden rule, though?
no, there's a much grosser approximation, which I kind of snuck by you. This is the Bourne Approximation. It's not just the Fermi's golden rule. That actually is not the worst approximation. There's a much worse approximation. I'll explain it right now. Here's the Bourne Approximation. This is the way to think of it. What we did was we have a scatter here, V of R. Now the idea is that we have an initial state. This is the way to think about it. I have an initial state. Now the initial state lives simultaneously in all of space, right? That's my initial state. Psi I is equal to e to the I ki dot r. And what I say is, at some point, I'm asking the question, what is the probability for my momentum to suddenly be in this state? Psi final is equal to e to the I k final dot r. And so we're doing transitions like this. I used to be in this state, and now, bing, I'm in that state. It's like I'm going, the potential's going from this state, bing, to that state. Okay, that's what we just calculated. All right, and we used time-dependent perturbation theory, and we went through all the math, and we got an answer. Now, really, in my mind, the biggest approximation here is that we're saying that the eigenstates are plane waves. And that's a really big approximation. That's false. Because look, the real eigenstate, I'm not going to derive it today, but we will derive it another day. And look, this is the real eigenstate, right? I mean, I got a potential, and I got these wiggly, I got these waves that are coming in, and then there's these waves that are scattering out, and then this is the real eigenstate, okay? It's like this weird superposition of waves going every which way, and they're all there's all these circular waves. Do you see what I'm saying? It's like the actual eigenstate is much more complicated, the true eigenstate. And we're not ready yet to talk about the true eigenstate. It's just too much for our minds to comprehend. Our heads will explode if we try to understand the true eigenstate at this point. But so instead, what we do is we ignore the true eigenstate, because it's like looking into the face of God and we'll turn to stone or something. And so instead, what we do is we just consider the eigenstate as these plane waves, because plane waves are simple and easy. Everybody loves a plane wave. What's not to like? We all love plane waves. And so we just say, okay, I got an initial plane wave, and then I have a transition to some new plane wave. Boom. And that's the Bourne approximation. And it works really good for a lot of things. So let's take a look at. The Bourne approximation is sort of the simplest to me. You know, it's everyone's simplest go-to scattering expression, and it works for a lot of things, but not for everything. But let's talk about where the Bourne approximation works, and let's try to understand the Bourne approximation a little bit more. Oops, I did something. So so let's talk about the Bourne approximation. There's something. So the Bourne approximation is quite beautiful. D sigma d omega is equal to, let's just write it down. It's so simple. I'll write it again, 4 pi squared h bar to the 4th times this. Okay, so this is why we like the Bourne approximation, because it's just so goddamn simple. Look at that expression, you know, it's just right there. All it is just some fundamental constants basically times this matrix element. The matrix element connecting the initial and final states when they are plane waves. That's what the Bourne approximation is, and we square that, and so we square that matrix element. And so you can see that the important part is that matrix element. And let's talk about that matrix element. So scattering. So the thing that controls scattering. So the scattering is controlled by the matrix element. And so let's take a closer look at that matrix element in order to see that there's actually a very beautiful physical interpretation of the matrix element that I want you guys to see, which I find very helpful. So let's write down the matrix element, VFI. The matrix element that connects the initial and final states in the Bourne approximation is this. I have an integral over space. It's, you know, it's this thing, you know, K final, V of R, K initial. And I'm not going to do that stupid tilde anymore. Let's just understand that the size of the universe is 1 for the Bourne approximation. Nobody does tilde. So let's write the wave function. My final wave function is, and it's a complex conjugate, e to the minus I K final dot R times the potential, V of R, times the initial state, e to the I K initial dot R, right? D cubed R. And this is the volume of the universe, right? I'm integrating it over the whole universe, right? All space. That's the thing. That's the important thing that determines whether the particle scatters. That this term determines the probability of scatter. The d sigma d omega is like the probability to scatter into a certain direction. All right, so what does this mean? Because when you look at this for the first time, it's just some bizarre integral that kind of makes no sense. Well, I mean, it's easy to write down. So let me rewrite it. VFI is equal to the integral of e to the minus I K final minus K initial dot R times V of R d cubed R. Okay, now look at it the way I've rewritten it. And this is, what is this thing? What is this thing that I have written? It's a what? Can someone tell me? It's a mathematical object that you've all seen 100 times before, and even more. Every single one of you has seen this. What is it? What is it called?
Is that like the Fourier Transform?
Yeah, 2 thumbs up. This is the Fourier Transform of V of R. That's right. So we're taking the potential and we're taking the Fourier Transform. And the Fourier Transform takes us into momentum space. And so I can call it, in using the language of Fourier Transforms, I can call it V twiddle of Q, where Q is equal to what? Can someone tell me? What does Q equal?
Kf minus Ki.
That's right. This is using the language of Fourier transforms, a language that you all have learned, although you probably have mostly forgotten it. But at one time, you learned it and you knew it quite well. You remember it, you memorized it for the test. But now you've probably forgotten it. Okay, but still, now I'm going to remind it to you though. This is the language of Fourier transforms. So what we have here is a Fourier transform, okay? So V of I is equal to the Fourier transform of the potential at Q, where Q is equal to KF minus KI. So there's a couple of things to think about here. First, let's ask ourselves, what's Q? What's the physical interpretation? Q, what is the physical interpretation of Q?
The change in momentum.
Yes. That's right, delta K, change in momentum. Change in momentum. Okay. What's now V of Q? What's a physical interpretation of the Fourier transform of V at Q? What does that mean? Is there a physical meaning to that?
Is it like how the potential affects particles with that change of momentum?
It is. I mean, that's you're right. That's the physical interpretation when we take into account the Bourne approximation. But I want to step back and I just want to say, what is sort of from a mathematical point of view, forget physics. Throw away all the physics, go back just to math. Mathematically, what is V of Q? Mathematically, but intuitively, how do I think of the Fourier transform at Q?
Doesn't it break it up into like the frequencies or something like that?
That's exactly right. Because what I say is, I say that V of R, the function, and the function can just be some funky thing like, here's my function, okay, a little dip, a bump in the road. This is called the bump in the road function. So that's V, that's R, it's a bump in the road. But we know, and you know, that I can write that as, it has that Fourier component, plus this Fourier component, plus this Fourier component, plus this Fourier component, and I add them all up. And that's what a Fourier transform is, just adding them all up. And so each of these is a V twiddle at Q. For this Q is equal to 2 pi over lambda, for whatever that lambda is, okay? So that's right. So this is telling me V of Q is basically telling me how much of the potential is basically telling me what is the amplitude of the potential at Q equals amplitude of potential at Q. It's basically telling me how much of the potential is sitting at this Q, where Q equals K final minus K initial. Now, the point is, and this is an important point, the d sigma d omega is proportional to this Fourier transform at Q squared. And that basically means that for scattering to happen, the scatterer has to have some component at Q. Basically, it has to have wiggles. It has to have wiggles at that momentum. So what that is telling us is that K initial has wiggles, right? It has the initial wiggles. And when I say wiggles, I mean, it's like that, it's a wiggly thing, right? K initial, it's a wave, it's a plane wave. K final has the final wiggles. Wiggles. Like that. K final. So one guy is wiggly like this, the other guy is wiggly like that. And then I have Q is equal to the difference in the wiggles, right? Is equal to the change in momentum. But for the scattering to happen, V of R has to provide those wiggles. the V of R provides the wiggles at Q, because the V of R has to have some component, V of Q, not equal to 0 for the scattering to happen. So the point that I want to emphasize to you is that the potential is providing the change in momentum. What does that mean? Can somebody?
So does this mean that for a given initial K, there's like a resonant KF?
This is, no, we're not talking about resonances, although it's sort of close to that concept. What is it? What is the physical interpretation of this? I have initial wiggles, and when I say the word wiggles, what does wiggles mean? In quantum mechanics, when someone says wiggles, what do they mean? What's the physical quantity associated with wiggles?
Waves.
That's right, waves, which is related to energy, which is related to momentum. That's the word I want you to. That's the word I want you to hear, to think of, momentum. When we talk about waves, we're talking about momentum. If I have shorter wavelength, I have higher momentum. And if I have waves in this direction, then I have momentum in that direction. If I have waves in this direction, then I have momentum in that direction. The wiggles and the waves are telling me give me all the, is momentum in quantum mechanics. That's what momentum is, it's wiggles. So I have an initial state where the wiggles are in this direction. I have a final state when the wiggles are in this direction, and something is providing me with the difference in wiggles. Who's providing the difference in the wiggles? Who?
Potential.
Yes, the potential. And I do not get to go, I do not scatter unless my potential provides the difference in wiggles. Doesn't that sound sort of eerily familiar? I got a momentum like this, and then I got a momentum like that, and the potential has exactly the difference in momentum. What is that called? What does that remind you of? What?
Conservation of momentum.
Yes, exactly. That's what I wanted you to say. We just derived conservation of momentum. Conservation of momentum.
I don't know if the screen's not writing anything, but I don't see you writing.
Why did that happen? I wonder. Damn it. That was so lame. Okay, let me do something then. What should I do? Maybe I'll stop the mirror. Okay, I'm gonna stop sharing and then reshare. Stop share. Are you guys all there? Oh yeah, share screen. It's so annoying. Okay, there it is.
We can see it.
All right. Okay, that's conservation of momentum. And I just want to say, because I want you to see it, you know, we have the initial momentum, Ki is equal to initial momentum, Kf is equal to final momentum, and V of R has to provide the Q, which is the difference in momentum, okay? And you don't get to scatter unless your potential has that difference. So the thing to think in your mind, the way for you to physically interpret this is that the potential is providing the momentum. That's the scattering momentum, okay? I have my initial, I got my final, and it's the potential itself had to have wiggles that gave me exactly the change in momentum. That is a very fundamental concept in quantum mechanics. And although it might seem really strange to you now, if you keep doing quantum mechanics, it won't. After like 10 or 12 years, it'll seem very normal. Maybe it'll only take you 5 years. Okay, so That's very important. And I just want to say that's about as close as you will ever get to conservation of momentum in quantum mechanics. This is conservation of momentum. This is where it comes from, okay? At least, you know, I mean, I've been using quantum mechanics for like 40 years, and in the 40 years, this is as close as it gets. You know, this is where conservation momentum comes from in quantum mechanics. It's right here. We just did it. So this is like an important moment in your life. Like, oh my God, I just conserved momentum in quantum mechanics. Energy conservation is, you've already been doing a lot of that, but you haven't done momentum conservation. This is it. This is momentum conservation. You just did it. Okay, now let's move on. Okay, great. That's momentum conservation. So now let's do a example. Let's do an example. Okay, enough abstract stuff. Let's actually do a real example. So let's consider a real potential. And this is actually a very important potential. Now, one of the most important potentials in the whole universe is the Coulomb potential. Coulomb potential. And the Coulomb potential is V of R is equal to, and I'm not going to worry about I'm not going to worry about all the little constants. I'll just call it V naught over R. Okay, so that's I'm not going to worry, you know, let's not get into all the constants. So that's a Coulomb potential, a 1 over R potential. Now, solving for the scattering off of a 1 over R potential turns out to be surprisingly difficult. So I'm not going to get into all those nuanced details. It's because it's just too long range. The math is really hard. But it turns out that in the real world, there really is never, like the 1 over R potential does not really exist out in the real universe. Can someone tell me why the 1 over R potential actually doesn't exist even though everyone has told you that it exists all your life until this moment? Why doesn't it exist? Can someone tell me why? The 1 over R potential is a figment of your imagination. It doesn't really exist. Everything everyone has told you up until this moment is a lie. Why is that? Can anyone tell me why? Physically?
Is it because you usually don't have the required symmetry?
I don't know, maybe. I mean, maybe, but I don't think so. I don't think there's a symmetry reason. The reason why I say maybe is because, you know, I'm not like super smart about symmetry. I mean, maybe there is some deep symmetry reason that I just don't know about, but I don't usually think of it as a symmetry thing. Can someone think of another reason?
Is it because the electromagnetic field is actually quantized?
Probably, maybe. Yeah, that could be. I think you're right. Yeah, I think that has something to do with it. But I want to even say something simpler because, you know, I like simple things. Okay, and there's a word which is called screening. Have you guys heard the word screening before? Screening. The thing is that there's always something that screens the potential. It's kind of like, it's sort of like if I have some negative charge here, and then if I have some positive charge around, then that negative charge will attract the opposite charge. It'll attract some of that positive charge, and that's called screening. And that always happens. There's always something that will screen, and it could be, you could be screened by monopoles, by dipoles, by quadrupoles. There's always something that screens charge. And when you talk about the quantization of the electromagnetic field, yeah, even in a vacuum where there's no other charges, you could have like fluctuations of the electromagnetic field that screen your charge. So let's not get into all those nuanced details, but I just want to emphasize that Coulomb potentials are always screened. 1 over R potentials are always screened. And what happens when you screen a potential, and I'm not going to derive this, but it's a very famous result that you derive in solid state physics. We derive it. I don't know what other classes you derive it in, but if you add screening to a Coulomb potential and you do a little bit of math, and I'm not going to do it because that's neither here nor there, then you end up with what's known as the Yukawa potential. And so the Yukawa potential is actually much more physical than the Coulomb potential. The Yukawa potential is the one that actually happens in nature, whereas the Coulomb potential is just sort of a figment of your imagination. So the Yukawa potential is written as V naught times 1 over R, but then something goes on top. Does anybody know what goes on top? Has anyone seen the Yukawa potential before? Okay, well, I guess not. This is your lucky day. It's an exponent. And so it might look really weird the first time you see it, but this is what it is. It's kind of like I have my Coulomb potential. Like, let's say if I have an attractive Coulomb potential where this is V and this is R. You see, that's a Coulomb potential, 1 over R, right? 1 over R. But then what you do is you multiply it times this exponent, e to the negative R over R. And so then it has a length scale. Length scale is big R. And that length scale is called the screening length. And the bottom line is that out past this screening length R, the potential goes to 0. The potential drops quickly. So for R less than big R, it looks like a Coulomb potential. But for R much bigger than big R, then it goes to 0. Okay? So the Yukawa potential is basically like a Coulomb potential that just dies off more quickly. It's just a Coulomb potential times an exponent. And it's actually very physical. It's even more physical than the Coulomb potential. And I just wanted to emphasize that because now we're going to do a bunch of math on it. And I want you guys to appreciate that this is actually a very important problem. And it's not just, we're not just dicking around. It's like we're not just playing around with the only problem that we can solve, even though it actually is the only one we can solve. It happens to be a very important one. Okay, so let's do a real problem then. Suppose I have a Yukawa potential here, and I shoot a bunch of quantum mechanical particles at it, like protons or neutrons or something, or well, protons, electrons, something that feels that Yukawa potential. And suppose I shoot them in with some luminosity. I'm at CERN. I'm doing a high energy experiment. I'm shooting at a number of particles per second per area. So I'm defining my luminosity because, I talked to the engineer at CERN and he told me what the luminosity is. And now I have some detector here that spans some solid angle d omega because I built that detector. I know how big it is. And then my question to you is, how many of those particles are going to go into my detector? dn equals what? And this V of R is a Yukawa potential, e to the negative R over big R divided by R. Okay? And so I'm giving you this, given the luminosity, I'm giving you this, I'm giving you the potential, and I'm asking how many particles per second go into my detector. So this is a very physical question, like an engineer, would ask, like how many? So I won't drag you through this little first part, but I just want you to remember we went over this from the classical theory of scattering. We know that the number of particles that go into my detector is equal to the luminosity times d sigma d omega times delta omega, the solid angle of my detector. Solid angle of detector. And this is my differential cross-section. And the point I want you to see and appreciate is that this is given. You're given the luminosity and you know the size of your detector, but the thing you don't know is d sigma d omega. How do we get d sigma d omega? How do we get d sigma d omega? Somebody tell me.
The Bourne approximation?
Yes, exactly. We use quantum mechanics. And the quantum mechanics we use is the Bourne approximation. And so that means then that using the Bourne approximation, d sigma d omega is going to be equal to this very simple formula, which is m squared over 4 pi squared h bar to the 4th power times that matrix element that connects my initial state to my final state. All right, so that's it. And so what we got to do then, you can see, we got to calculate that matrix element. And so if we want to know the d sigma d omega, we got to find that matrix element, and that matrix element, of course, is the Fourier transform. So let's find that. So let's find that Fourier transform. dFi is equal to the Fourier transform. So it's going to be, and I already wrote it, so I'll just jump to this form: e to the minus I kf minus ki dot r times v naught e to the negative little r over big R divided by r dq r. Okay, so we got to do this. This is a Fourier transform. Okay, so that's what we got to do. We got to calculate this Fourier transform. And this wave, I just want to point out that this wave that that's the e to the I q dot r, and that's the transferred momentum. So we're basically looking at the wave that's associated with the transferred momentum, which is the transferred momentum, and we're basically saying how much of that wave, of that transferred momentum, is living inside of the potential. That's what Fourier transform tells you. So that, I just want you to realize that that's what we're doing. So, but now it's a math problem, okay? How do we do this Fourier transform? And actually it's a pretty hard problem. I think what I'll do is I'll try to set it up for you a little bit. It's a famous integral, because this integral pops up in some other parts of physics. It's a famous integral, and so you got to. So let's do it. So there's some geometry. So I want to set it up for you because you can see it in your book, but it's kind of confusing when you see it for the first time. So let's just remember the scattering geometry. I got my initial K, I got my final K, and then I got this scattering angle, which is theta, okay? And so that means that I can redraw it like this. I see that I got a initial K, I got a final K, and here I can draw this. This is my scattered K. That is my K final minus K initial, right? That's my Q. My transferred momentum is that one that I just drew. What can I say about the length of KF related to the length of K initial? We discussed this already. What's the relationship between those guys? What is it? How are they related?
They're equal?
Yes, because we assume it's elastic scattering. Energy is conserved, elastic scattering. You've heard that term before. But the KF minus KI, that could be quite different. So let's take a look at this geometry. So we got this geometry where this is KF and this is KI, and this is the scattered momentum, KF minus KI, is that arrow. And I want you to notice something. If I look at the lengths of these arrows, this angle is theta, but this angle is what? If I drew that at the bisecting angle, what is that little angle? Can someone tell me?
Theta over 2.
Yeah, it's just pure geometry. It's theta over 2. And so what that tells me then is that, and that means that this little distance here, what is that little distance equal to? I have a right triangle here, see? Well, I'll just tell you the answer. It's going to be Ki sine theta over 2. Do you guys see that? Just a simple little trigonometric trick. And so, but what we're going to do is let's call Kf equals Ki. Let's just call that K. Because K is something that's given in the problem. because K, remember, is given in terms of the energy. When someone gives you the length K, that's the same as them giving you the energy, because there's this relationship, right? Because energy is equal to h bar squared K squared over 2m. And so K is equal to square root of 2mu over h bar. So K is known. So this thing then is K sine theta over 2. So that means that the length of this kf minus ki vector is equal to 2k sine theta over 2. Oh my God, that's pretty tricky and clever. It's simple when someone shows it to you, you know, it's just trigonometry, but it's the kind of thing where you would go, you'd never have thought of it on your own. But now that I show it to you, you can just see it's just a geometrical construction. So so obviously the length of kf minus ki is 2k sine theta over 2, where theta is the scattering angle. It's this theta. It's the scattering theta. Okay, that's it, the scattering theta. Okay, so what that means then is that I can replace in this integral, I can replace this with e to the minus I, the length of kf minus ki times the length of the r vector, which is just r, times the cosine of the angle between them, which I'll call theta prime. Do you see that? But this is all getting kind of tricky. What is theta prime? What is theta prime?
Theta?
Okay, well, theta prime is the integral, because is the integrating angle. Because now let's draw it all out, because here's, okay, let's do this now. Let's draw it, because the geometry is getting really complicated. So the trick, here's the big trick. The trick to drawing it is that I have to say that let's let kf minus ki be the direction of the z direction for the spherical integral, because this integral is a spherical integral. And so the trick is this. And so once we do that, then everything becomes kind of simpler, because now we have this vector r prime. And so you can see that then this, if my integrating symbol, if my integral is the primed coordinate, then what I have is, I have VFI is equal to, well, I'll draw it both things. It's going to be this e to the I to the minus I, kf minus ki dot r, and I'll call this the primed coordinate, times v naught e to the negative r prime over big R over r prime times d cubed r prime. So we're integrating over the prime coordinate. And so now when I do this trick, I'm going to say that integral is now equal to e to the, and this is going to be my theta prime, and this is going to be the direction of kf minus ki is in this perpendicular direction. Maybe that's getting a little too confusing. I'll just say that it's proportional to z hat. And so this integral turns into this. It turns into a triple integral where I'm integrating over phi, theta, and r prime, the prime coordinate, and it'll be e to the negative I 2k sine theta over 2, because that is the length of k final minus k initial, times r prime cosine theta prime, because I have that in my integrate in my new coordinate system, times e to the negative r prime over r over r prime squared dr prime sine theta prime d theta prime d phi prime. Whew, okay, that's the integral. And it turns out that this integral is really actually pretty, you can do it now, because the next trick is a change of variables. What you do is you say u is equal to cosine theta prime, and then du is equal to negative sine theta prime d theta prime. And so that is going to help you with this part. And because that's the only hard part now, and it's going to help you with this part. So that's going to be u, and that's going to be du. And so you can see that this change of variables helps you. I'm not going to do any more of the math because it's just too much. I don't have time for it. But now you guys can do the rest. Do the rest, and it's not hard. And it's also in your book. I think it's in Griffith's somewhere. So you can do that, and then what you're going to get is that you're going to see that this VFI, the absolute magnitude, is equal to, after you do these integrals, which now are not that hard, but just a little bit of tedious algebra, is 4 pi V naught r squared times 1 over 1 plus 4 k squared big R squared sine squared theta over 2. So you get this beautiful answer. And then when you plug that in, then you're going to get that the differential cross-section d sigma d omega of the Yukawa potential for the angle theta and at energy E is going to equal m squared over 4 pi. Oh wait, let's erase that. It's going to equal 2m v naught big R squared divided by h bar squared times 1 over 1 plus 4 k squared big R squared sine squared theta over 2, and that quantity squared. Okay, so that's what we get when we do the math, all right? That's the differential cross-section of the Yukawa potential. And the reason I say E is because K is equal to square root of 2me over h bar. So wherever I see a K, that actually stands for E, okay? So let's plot it. And let's consider two extremes. High energy, and low energy. Let's do the high energy scattering. High energy. High energy means that we have big k squared, okay? And when the k squared is big, then let's plot out this formula. Look at the formula, you see it right there. You know, here's the formula, there's an arrow at it. If k is big, then I have these two parts in the denominator. I got the constant and this other part, and you see that the k squared part dominates at high energy. So at high energy, my formula reduces to d sigma d omega is equal to, what is the expression at high energy? At high energy, it reduces to this. You can see that it's going to be proportional to it's proportional to 1 over k squared. And so if I plotted it, d sigma d omega, then you see it's highly peaked at theta 1 over k squared sine squared theta over 2. And so if I plot it as a function of theta, you see it's highly peaked at low theta, okay? Because sine theta, as theta gets bigger, then it starts falling off. Because this is 1 over sine squared theta over 2 is peaked at theta equals 0. You see that? Because when theta is 0, it's 0. And so this function is highly peaked at theta equals 0. Now, I just want you to think about what that means for a moment. What that means is that if I have a potential V of R, and if I shoot the particle in, then d sigma d omega only is non-zero for theta equal to 0. That means that the particle wants to go straight. Now, it's like no scattering. Because if I have a little bump in the road and a high energy particle, it doesn't see the scatter, it just blasts right by it. But on the other hand, if I do the low energy, and then we'll be done because it looks like we're running out of time, low energy, for low energy scattering, then k squared is small. And when k squared is small, when I look at that formula, I have that d sigma d omega is equal to a constant. You see, because the k squared part is small, and all I have is that 1 left over there. And so it's equal to a constant. But if d sigma d omega is a constant, if I plotted d sigma d omega as a function of theta is a constant, then what that means, that's equivalent to saying that if my particle comes in with some k initial, it has equal probability to go into any direction. And so this is strange. This is a quantum mechanical effect. This is very non-classical. And the reason that this happens, if you go through all the math and think about it really hard, then what you'll see is this is what's happening. Basically, I have a long wavelength wave is coming here. It's hitting this fuzzy potential, and it's wrapping itself around that potential, and it's scattering outward. So I got a wave going in, and then I got the wave going out. So this is the long wavelength. It's really diffraction. You guys have thought about diffraction before, but that's what it is. It's like the wave is wrapping itself around the scatterer and scattering out. It's diffraction. This is diffraction. Okay, so we got to stop. Okay, guys. Bye-bye.
Thank you.
Okay.